This is Tech and Politics, and I am Andreas Jungherr. Welcome back to the podcast accompanying the lecture series Digital Media in Politics and Society at the University of Bamberg. In this and the following 3 episodes, we will discuss the role of data in politics and society. Data are crucial for the discussion of politics and digital media. Understanding the core concepts and issues arising from the quantification of social and political life and the resulting data is important for engaging in many of the subsequent controversies of the uses of digital media in politics. Digital media, devices and sensors collect data documenting the world, society and human behavior. This has been seen by some as a measurement revolution, providing many new avenues for the social sciences as well as new business opportunities in the economy. Perceived potentials and dangers in the increases in the volume and breadth of coverage of digital data are broadly discussed, but it is also important to examine how these new data sources relate to the social or behavioral phenomena they supposedly cover. New data riches have to be translated into meaningful measures of phenomena of interest and society. Digital data provide the newest step in the quantification of reality and social life. This leads to 3 important questions that need to be addressed in research. How do we turn the world into numbers? What do these numbers enable us to do? And how do we, as a society, structure this process and define rules and regulation of what is and is not allowed? These are powerful questions framing research projects, and they will help us structure this session. This session on data will start by presenting core issues arising from the quantification of social and political life. Following this, we will discuss the hopes and limits connected with the term big data. This then will be followed by the discussion of fundamental questions of scientific measurement. Once these foundational concepts and questions are discussed, we will discuss how political organizations and other actors are translating the world into data and are using data to better understand their environment, the effects of their actions, to control their members, and to improve their work. This then will form the basis of discussing the trade-offs between increasing the capacity of organizations and states through data and the considerable privacy concerns of people whose data are collected, processed, and potentially shared with others. This and the following 3 sessions will introduce students to core issues of data collection, use, and governance through digital media and devices. They will learn core concepts in the discussion about data and measurement, and will encounter key examples and trade-offs that need to be considered in the examination and discussion of data uses by political organizations and actors, and the governance of data collection and data use through regulators and the state. But let's start by looking at data and quantification. Computation and digital media have reinforced interest in the opportunities and challenges of data and quantification in various societal fields. Data promise the objective observation of the world, insights into hidden patterns and causes, and foresight into future developments or the outcomes of specific choices or interventions. Data are crucial for making the world legible and changing it through targeted interventions. In this sense, data provide the basis for the modern world and its scientific understanding. Digital media and computation have increased the availability of data in ever more fields. They also have extended analytical opportunities. It is no surprise then to find digital data to be a topic of both enthusiasms as well as fears. But before we can take a closer look at both hopes and fears, we first have to be clear about what exactly we mean by the term data and what the preconditions are for data providing a true representation of the world. Let's start with the definition of data. Data are symbolic representations of entities in the world and their relationships. They are the result of some measurement process that maps entities' properties to numerical values of a variable. The numerical relationships between variables represents the relationship between entities in the real world. This definition points to important features of data that make them useful, but also constitute limits to their use. Data provide reduced symbolic representations of specific characteristics of entities of interest. Numeric symbolic representation allow the documentation of entities, events, or behaviors. Mathematical calculation allows the identification of causal or correlative connections between recorded entities. Models developed based on these connections allow the prediction of likely outcomes given specific inputs. Data are therefore an important feature that allows for a deeper understanding of the past, control of the present, and even provide a glance of the future. But to do so, we first must translate entities of interest in the world into reduced symbolic, numerical representations. This process is called quantification. We can define quantification as referring to the process of translating entities or selected characteristics of entities into numbers. Quantification, the reduction of entities to numbers, is powerful. It allows to document past and present, as well as to plan for the future without having to account for the richness of entities in the world. The translation of entities of interest into numbers provides a model of entities, their relationships, and potentially the world. It also allows for the performance of mathematical operations. These operations do not only speak to the numeric representation, the model, but also allow for inference on the underlying entities and phenomena, potentially uncovering otherwise hidden patterns and causal relations, or the prediction of future developments or effects of interventions. Data not only represent the world, but also allow for targeted interventions. While quantification offers impressive new opportunities, it also carries limits. In reducing entities in the world to numbers, quantification reduced the world to countable signals. This means disregarding much of the world. This can be useful, but this can also be dangerous. In the process of quantification, unimportant features of entities might be counted, while important might be missed or disregarded. Or, in the process of reducing entities to numbers, their essence might be lost. Accordingly, anyone working with data will have to consider the underlying data-generating process and, if necessary, critically interrogate it. We will return to this when we'll be looking at measurement. Also, quantification not only represents the world. In some sense, it is recreating it. Quantification assigns entities, or selected features, to categories. These categories then become the structuring devices people use to learn about the world and shape it through interventions. The definition of categories and the interpretative mapping of entities and features become important constitutive features to data-driven reasoning. While the analysis of data follows objective rules of probability and mathematics, the process of defining categories and assigning entities is constructive and interpretive. Accordingly, these aspects of quantification need to be subject to critical interrogation. Quantification and resulting data promise insights about past, present, and future. But to distill information from data, we must not only analyze data and their inherent relationships. We also need to actively account for limits of quantification and measurement approaches in relation to our interests. Otherwise, even the most impressive efforts in quantification and quantitative analysis will lead to mistaken views about the world. Digital media and digital technology more broadly have provided society and researchers with new data sources that appear to be cheap and ubiquitous. In the past, collecting data was difficult and expensive. People had to go actively out, count, and record their objects of interest. In social science, they had to run expensive surveys in which people visited or called respondents and had them answer questionnaires. This made data expensive to collect. Digital technology changes this. Existing analog datasets are digitized and thereby made broadly available and accessible for computational analysis. At the same time, digital technology collects original data continuously. Examples include digitally enabled sensors that collect information about the environment and translate signals into data. Sensors like this can be found in cars, mobile phones, and many internet-enabled smart devices. Additionally, people's interactions with digital services create data traces, documenting their behavior. These data are collected and used by device makers and service providers and can serve as basis for the improvement of existing devices and services or the creation of new ones. While these data sources are primarily available to commercial actors, academics can gain access to selective slices of these data through standardized open protocols, such as application programming interfaces, APIs. Those define rules and limits of public data access. Or researchers can engage in privileged collaboration with companies. Digital technology thus promises a new data abundance for business, society, and academia. Data are suddenly cheap. This created a lot of enthusiasm among business consultants, journalists, and some scientists about the supposed potentials of unknown data riches. The term big data has become the focus point of these enthusiasms. Originally, the term big data refers to large data sets that technically could not be held or processed in one database or on one machine. But soon it gained popularity as a term covering the new data riches provided through digital technology and the associated economic benefits. One of the earlier characterizations of big data was proposed by the business consultancy Meta Group and, after its subsequent acquisition by the consultancy Gartner, has become known as the Gartner definition. This definition goes like this. Big data is high volume, velocity, and variety information assets that demand cost-effective, innovative forms of information processing for enhanced insight and decision-making. Since the original formulation of this definition in 2001, many additional Vs have been suggested and covering new or unobserved characteristics of big data. But the original 3 Vs, volume, velocity, and variety, should suffice for our purposes. They illustrate the suspected promises of big data very clearly, while also pointing to one of the crucial shortcomings of subsequent efforts and debates. The definition points to its origin being interested in the technical issues arising from handling datasets made available through digital technology. Data come in great volume, surpassing the capabilities of standard computational setups and statistical methods. Data come in great velocity, on the one hand allowing for real-time analysis of unfolding phenomena, but at the same time also providing challenges by shifting features within the data and data-generating processes. Finally, data come in great variety, such as text, image, video, audio, or metadata. As a consequence, data need to be structured in order to allow for subsequent analysis. The definition puts its focus clearly on the technical features of big data, and not their characteristics as a representation of objects in the world. This can be forgiven, given the definition's origin, with a technical consultancy trying to prepare its clients for future opportunities or challenges. Unfortunately, the same focus on technical features, simplistic fascination with the size and volume, and an overwhelming disregard for issues arising from the translation of entities in the world in symbolic representation has dominated the subsequent debate and use of the term. This is much less forgivable. Nearly all discussions of big data treat them as true representations of whatever is of interest to the speaker. This could be buying intentions, psychological traits, or political affiliations. Whatever happens to be in the desire of the inquirer, big data shall provide. If we would follow the big data boosters, we could expect to find everything and all in big data, no matter what we are looking for. This is, of course, not the case. But goes for other types of data, also holds for big data. The translation of entities into symbols entails the construction of their representation. Quantifying the world depends on creatively translating objects of interest into measurable signals and translating those into data. These important interpretive steps are just as important in the age of big data as before. Arguably, it is even more important now than ever, since people now have access to data not primarily collected with their analytical goals in mind. To mobilize the potential of these found data for research demands for very active and creative steps in quantification. Let's take a look at one of the most prominent and talked about categories of big data: digital trace data. In 2011, Hausen and colleagues defined digital trace data as, and I quote, records of activity, trace data, undertaken through an online information system, thus digital. A trace is a mark left as a sign of passage. It is recorded evidence that something has occurred in the past. For trace data, the system acts as a data collection tool, providing both advantages and limitations. End quote. Examples for digital trace data include messages and metadata, documenting contributions, behavior and interactions of users of social media services like Twitter, Reddit, or YouTube. Due to their comparatively easy accessibility through application programming interfaces, APIs, data like these have become prominent in the work of social and computer scientists. Additionally, they provide the basis for many consultancy and media analysis services. Digital trace data, therefore, have come to provide representations of social systems and human behavior for academic work, as well as professionals in media and other businesses. But there are specific challenges to symbolic representations of the world based on digital trace data. While early enthusiasts expected digital data sources like these to provide all-encompassing insights into human behavior and social systems, time has surfaced severe limitations and sources of bias. Two sources of bias are especially relevant in working with big data built from digital trace data. These are biased coverage and biased behavior. Let's define bias in datasets. A bias in datasets refers to a systematic error or deviation from a representative sample. It occurs when a dataset doesn't accurately represent the population or domain it claims to, leading to skewed results. For example, a dataset claiming to represent the general population would be biased if it primarily consisted of individuals between the ages of 18 and 36. Data collected by digital services, while high in volume, are still limited by who is using the services to begin with. This means that the active user base of a digital service determines the share of life that can be covered by data collected on that service, and that can meaningfully be quantified and modeled through that. The active user bases of even the biggest social media services are highly concentrated within specific demographics and systematically exclude specific social demographic groups. This is true for age, by systematically underrepresenting older people, but potentially also for political leaning, with different services catering to partisans of different political leanings. Some of these biases in the coverage of these datasets can, in principle, be identified. Others remain hidden, be it for lack of information about users, or be it for unobserved shifts in the composition of the user base contributing to a given data source. There's also the risk of measuring biased behavior through digital trace data. Digital trace data only offer us access to behavior of people mediated through the affordances, interfaces, and code of the providers of digital services. For example, we might be interested in the attitudes of Twitter users, but the only thing we get is their public posts. These might be true expressions of opinions, thoughts, and reactions, but they might just as well be the results of a strategic public performance, in where users play a public role and post fitting messages. Or they might be the result of behavioral incentives provided by the services themselves, such as algorithmic content selection. These are just a few examples for how the information system recording and providing data is also shaping data. So in the end, we cannot be sure that we measure human behavior beyond the digital environment it was collected in. For the purposes of using the data for inferences beyond these confines of the generating process, the data therefore is clearly biased and unsuited. These limits of digital trace data, and big data more generally, are beginning to feature more clearly in the debate. Early on, these concerns were largely ignored in a spirit of daring can-do. But over time, the limits of work based on data like these became more apparent. Also, the more these data came to matter beyond the confines of academia, the more accuracy of diagnoses and prediction based on these data came to matter. An important factor in this was the growing use of large data sets in applications and services enabled through artificial intelligence. The richness and volume of newly available digital data is a core contributor to recent advances in artificial intelligence. With the growing awareness of AI-enabled opportunities, as well as associated risks, biases in datasets have received increasing attention. At the core of associated concerns are fears of biased datasets leading to biased outcomes of decision-making based on them. Especially automated algorithmic learning and decision-making have received much attention in this process. Questions of who and what gets counted in big data are thus increasingly getting more attention. Still, there remains much to do to overcome the current naive positivism in the work with big data. One core issue in the work with big data and in quantification in general is how the entities in the world get translated into symbols. This brings us to the question of measurement, which is the topic of our next episode. So, that's it for now. In the next episode, we will focus on measurement and its impact on data quality. As always, the script to this episode can be found online on the course website digitalmedia.andreasjungherr.de. There, you will find detailed sources, references to further reading, links, and preparatory questions for the exam. This was Tech and Politics, a podcast by the Chair for Political Science, especially Digital Transformation, at the University of Bamberg. I'm Andreas Jungherr. Have fun reading, and see you soon.